We will begin our opening ceremony in 2 minutes. Assalamualaikum warahmatullahi wabarakatuh and a very good morning to Yang Berbahagia, Dato Technologist Dr. Haji Amirudin Abdul Wahab, Chief Executive Officer, CEO, Cybersecurity Malaysia, Associate Professor Dr. Muhammad Rezal Datuk Kamil Arifin, Director of Institute for Mathematical Research, INSPAM, University Putra Malaysia, UPM, Associate Professor Dr. Suryati Paiman, Head of Physics Department, Faculty of Science, University Putra Malaysia, UPM, Associate Professor Dr. Hishamuddin Zainuddin, Advisor for Physics Without Frontiers, Expository Quantum Lecture Series 2020, Dr. Chan Kartim, Chairman of Physics Without Frontier, Expository Quantum Lecture Series 2020, distinguished speakers, university senior officers, respected delegates, and guests. Ladies and gentlemen, welcome to the opening ceremony of Physics Without Frontiers Expository Quantum Lecture Series 2020 EQuaLS2020. Now, I would like to invite Dr. Chan Kartim, Chairman of EQuaLS2020, to deliver the welcoming address. Please welcome Dr. Chan.
Thank you, Mr. Sorry. A very good morning to Yang Berbahagia, Dato Technologist, Dr. Haji Amirudin bin Abdul Wahab, Chief Executive Officer of Cybersecurity Malaysia, Associate Professor Dr. Muhammad Reza Kamil Arifin, Director of Institute for Mathematical Research, INSPAM, UPM, Associate Professor Dr. Suryati Paiman, Head of Department of Physics, University Putra Malaysia, Associate Professor Dr. Hishamuddin Zainuddin, Advisor to PWF EQuaLS2020, Dr. Kate Saw, Main Coordinator for PWF Program, International Center of Theoretical Physics, Italy. Speakers, colleagues, ladies and gentlemen. Welcome to Physics Without Frontier Expository Quantum Lecture Series 2020. It's a pleasure to be able to organize EQuaLS once again, despite the ongoing COVID-19 pandemics. So I hope everybody is taking appropriate measures to protect yourself and also others from this pandemic. So for your information, this event is basically jointly organized by INSPAM, Department of Physics from Faculty of Science, University Putra Malaysia, and also ICTP. This is basically very important to us because it marked our first collaborative effort with ICTP, blending the well-known PWF outreach program and also the highly anticipated EQuaLS program together. So it's an honor to be able to chair this event with Dr. Kate. So thank you, Dr. Kate, for this opportunity. Thank you very much. Ladies and gentlemen, so this year, the theme for EQuaLS is basically quantum informations from theory to technology. This is basically in line with the initiative of INSPAM Cybersecurity Partnership in promoting Malaysia into quantum era. So we are fortunate to have CEO of Cybersecurity Malaysia, Dato Dr. Amirudin today to officiate this event later on. So thank you, Dato, for being able to be with us today. So what is quantum information science? Quantum information science is basically the study of information science under the effect of quantum theory. So the history basically can be traced back to early 1960, where Stephen Wisner proposed to create a form of money that basically cannot be counterfeited due to quantum theory. So due to his work, it actually managed to stimulate the emergence of quantum information science in 1980s and also 1990s. So over the last decade, basically we can see that there's a rapid development in quantum information technology. So just for example, last year, Google actually claimed to have achieved quantum supremacy with their 53-qubit quantum computer, where they perform a series of operations in just 200 seconds. So if this kind of operations, we perform it on classical computer, this would actually take approximately 10,000 years. So seeing how quantum information science will basically change the landscape of information and communications technology in the future. So this is the reason why we decided to organize the 9 equals, particularly in this area. So ladies and gentlemen, it is my pleasure and honor to have a panel of distinguished speakers here today to share their knowledge in this area. So some of the speakers, they are basically from different time zone and they have made great efforts to be with us in this 5 days event. So hereby, I would like to offer my sincere appreciations to our distinguished speakers. I would also like to take this opportunity to thank the local organizing committee for their contributions in planning and also coordinating this event, especially during this pandemic. So last but not least, I'd like to thank our sponsor, Quantum Yijin Sendirian Berhad, Cita Education, Persama, as well as our media partner Majalah Science for their unwavering support in this event. So by the end of this event, I hope participants will somehow gain some knowledge on quantum informations. Finally, I wish all participants to have a wonderful and meaningful school. Thank you very much.
Thank you, Dr. Chan, for the speech. Moving on, I would like to call upon Dr. Nurisha Muhammad Shah, representing Dr. Kate Shaw from the Abdul Salam International Center for Theoretical Physics, ICTP, to deliver her speech. Please welcome Dr. Nurisha.
Thank you, Mr. Faris. Assalamualaikum and a very good morning to Yang Berbahagia Datuk Technologist Dr. Haji Amirudin bin Abdul Wahab, Chief Executive Officer of Cybersecurity Malaysia, Associate Professor Dr. Muhammad Rizal Kamal Arifin, Director of Institute for Mathematical Research in SPAM UPM, Associate Professor Dr. Surati Paiman, Head of Department of Physics, Faculty of Science UPM, Associate Professor Dr. Hishamuddin Zainuddin, Advisor to PWF EQuaLS2020, Dr. Chan Kartim, our Chairman of PWF EQuaLS2020, distinguished speakers, colleagues, ladies and gentlemen. Welcome to the Physics Without Frontiers Expository Quantum Lecture Series 2020. The coordinator for Physics Without Frontiers program, Dr. Kate Shaw, could not be with us today, but instead we were given the task on behalf of ICTP to say something about ICTP and Physics Without Frontiers PWF program under which today's event EQuaLS2020 is a part of. With the tagline of cutting-edge research, education and training, the Abdul Salam International Center for Theoretical Physics, ICTP, has been a driving force behind global efforts to advance scientific expertise in the developing world for more than 50 years. Founded in 1964 by the late Nobel laureate Abdul Salam, ICTP seeks to accomplish its mandate by providing scientists from developing countries with the continuing education and skills that they need to enjoy long and productive careers. Since then, ICTP has been a major force in stemming the scientific brain drain from the developing world. Ladies and gentlemen, To accomplish the aim of promoting cutting-edge research, education, and training, ICTP has been working on providing several programs and specific projects that can help to foster the growth of advanced studies and research in physical and mathematical sciences, especially in support of excellence in developing countries. And Physics Without Frontiers, PWF, is one of it. In general, PWF is a worldwide physics outreach programs that cover several outreach programs, such as PWF University Course, PWF Schools, and PWF Roadshow. PWF works to inspire, to train and motivate physics and mathematics university students worldwide with some focus on science and technology, lagging countries, and also to help build the next generations of scientists. Each project is unique, developed with the country's specific needs in mind. PWF organizes projects working with volunteer scientists who are PhD students, postdoctoral researchers, or lecturers from all over the world who are passionate about promoting and supporting physics and mathematics. Until now, PWF has worked with over 6,000 students worldwide in 20 different countries. In the present event, INSPAM, together with co-organizer Department of Physics, Faculty of Science, University Putra Malaysia, have successfully secured the PWF Schools project, for which EQuaLS2020 with the theme Quantum Information from Theory to Technology is a part of. The topic covers fundamental and advanced topics in quantum information, targeting over 60 advanced undergraduate and early postgraduate students. Of course, organizing the school in a virtual platform is a first time in the history of PWF, and thus it's definitely challenging. However, I strongly believe that getting a support from highly experienced speakers in the area, this event will be a success. Also, with the current trend of research and discoveries in the quantum information science and technology area, the choice of these particular topics is highly suitable for the participants in Malaysia. Therefore, congratulations to the local organizer. On behalf of PWF, I personally thank Ms. Shalawati Tiansen, who have been the key person initiating the PWF EQuaLS2020. Sheila did most correspondences with Dr. Kate Shaw in co-organizing PWF EQuaLS2020. I would also like to thank the distinguished speakers who have managed to find time to be part of this event, especially during this difficult period of COVID-19 pandemic. Lastly, I hope PWF EQuaLS2020 will be a success and that all participants will benefit from the school. All the best and thank you.
Thank you, Dr. Nurisha, for the speech. Ladies and gentlemen, please join me to invite Yang Berbahagia, Dato Technologist Dr. Haji Amirudin Abdul Wahab, Chief Executive Officer, CEO, Cybersecurity Malaysia, to deliver the officiating speech and to officially launch INSPAM CSM My Quantum Wave Initiative 2021 to 2025. Please welcome Dato Amirudin.
Dia Dr. Muhammad Rizal Kamil Arifin, Pengarah Institut Penyelidikan Matematik INSPAM, Universiti Putra Malaysia UPM, yang berusaha Profesor Madya Dr. Hishamuddin Zainuddin, Penasihat PWF Expository Quantum Lecture Series 2020 atau EQuaLS2020, yang berusaha Dr. Kate Shaw, Penyelaras Utama ICTPF Physics Without Frontiers, yang berusaha Dr. Chan Khatim, Pengurusi PWF Expository Quantum Lecture Series 2020 EQuaLS2020. Ladies and gentlemen, Assalamualaikum warahmatullahi dan salam sejahtera dan salam prihatin. For the benefit of our foreign guests, please allow me to continue in English. First and foremost, I would like to express my gratitude to the Institute of Mathematical Research, or INSPAM, University Putra Malaysia UPM, for inviting me to officiate the Physics Without Frontiers Expository Quantum Lecture Series 2020, or EQuaLS2020. I would also like to congratulate the organizers for making this event a reality. I was told that this program is a collaborative effort involving the International Center for Theoretical Physics, Physics with Officiation in Italy, and the Institute of Mathematical Research in SPEM of UPM, as well as the Faculty of Science, UPM. Congratulations to Associate Professor Hishamuddin Zainuddin as the advisor and main coordinator of the local organizing committee for pulling this event together. I am delighted to welcome our distinguished guests, speakers, and participants to the annual event. As we are all aware, due to the travel restrictions resulting from the COVID-19 pandemic, EQuaLS2020 will be held online. Ladies and gentlemen, quantum technologies and sciences is one of the fields that has been prioritized and has become popular among prestigious universities and research institutes abroad. Quantum technologies is considered as one of the disruptive technologies in the fourth industrial revolution and described as the advent of cyber physical systems, pushing entirely new capabilities for people and machines in the future. In aspects of Malaysia stand in adapting quantum technology, we are sharing the same ground and we are hoping to see it spearheads the science, technology, engineering and mathematics or STEM field in Malaysia. EQuaLS, which stands for Expository Quantum Lecture Series, has been hosted by INSPEM since November 2007. This time, together with the International Center for Theoretical Physics or ICTPF, EQuaLS is held again after almost 5 years. The primary objective of the lecture series is to rapidly introduce students to frontier topics in quantum information by inviting international prominent researchers in the relevant area. Quantum information science is a discipline right at the intersections of physics, engineering, computer science, and mathematics. Although this branch of study is still not synonym in Malaysia, but the discipline is presently matured enough to produce new quantum technologies. Other than giving out lectures, participants is also being introduced to working and research opportunities that are available in the field. It is with hopeful heart to see our young generation to not shy away from quantum science. I strongly believe that this 5-day lecture series will play an important role in pioneering the Malaysia into quantum era initiatives as to introduce quantum information to our local students and researchers. In light of the recent pandemic, we should still soldier through and put our best effort to keep scientific programs alive. Ladies and gentlemen, since 2017, corporate consumers and governments have been catching up with applying quantum technology in sense of data security. For instance, Acronis, a data backup company, has been using quantum random number generators for keeping personal, companies, or governments' data safe from any prying eyes. This is in contrast of any classic random number generators that having patterns of randomness that is based on their software program. This data security is only a drop in the ocean as to what quantum science have to offer. To name a few, giant corporations such as IBM, Google, and Intel has been on sprint in seeing quantum computers to life. The United States governments have also recognized the value of quantum information science and has come up with the National Quantum Initiative Act, which aims to accelerate quantum research and development for both economic and national security purposes. Our neighboring country, Singapore, through Center for Quantum Technologies or CQT, has also been making progress in developing quantum technologies seasoned by the international collaboration. Hence, it is time for Malaysia to start realizing the significance of quantum technologies. It is important to make this as a collective effort, where academics and industry to join hands in sprinting towards establishing a solid framework to pursue these promising technologies. Ladies and gentlemen, research and development or R&D in quantum technology is important. Cybersecurity Malaysia acknowledges the effort and provide endless support towards aspiring researchers to further their research in quantum fields. The Institute for Mathematical Research of University Putra Malaysia, or INSPAM, through their 2020 to 2024 blueprint and INSPAM Cybersecurity Malaysia partnership for the 12th Malaysia Plan RMK12, has come up the initiatives to improve both quality and visibility of the Institute in leading research in Malaysia. One of the initiatives is establishing My Quantum Waves. This particular initiative will provide a platform for knowledge transfer and discussion between experts and researchers on fundamental level of both theoretical and application of quantum science. INSPAM also would act as one of the hubs and center of excellence in Malaysia for any quantum-related projects in the future. This partnership would benefit both organizations as we holistically approach quantum technologies by sharing expertise from industry and academic. Other than R&D, experts and researchers in quantum must work together to expand network and communications. Therefore, EQuaLS2020 today provides a great avenue for information sharing and to showcase new technology in suits the theme chosen, quantum information from theory to technology. Ladies and gentlemen, we are lucky to have INSPAM as established research center to spearhead this quantum initiative in Malaysia. INSPAM, as many of us already know, has been actively collaborating at international level. One of INSPAM's long-term collaboration is with Politecnico in Torino, which will set up a Malaysian-Italian Center of Excellence for Mathematical Science, or MISEMS. INSPAM, through their theoretical physics group, also has been making continuous effort in preparing our young researchers to actively play roles in quantum science by organizing numerous international symposiums and seminars that focusing on advanced level of theoretical physics. Major players in quantum communication technology are also looking for collaboration with international partners to set up regional and intercontinental quantum networks and possibly even a quantum internet. Malaysia will do well in collaborating with regional major players in setting up such quantum networks. Ladies and gentlemen, before I end my speech, once again, I would like to thank all speakers for sharing these valuable knowledge and experience throughout this lecture series. I am certain that today's event is an excellent platform to realize research and applications of quantum technologies in Malaysia. Finally, congratulations to the Institute of Mathematical Research INSPAM of University Putra Malaysia and Faculty of Science UPM, as well as the International Center for Theoretical Physics, Italy, for having this school and all supported sponsors. This collaborative effort is very commendable and should be continued in the future. On that note, I hereby declare Physics without Frontiers Expository Quantum Lecture Series 2020 officially open. Before we end, I am pleased to also launch one of the initiatives through future collaboration by Cybersecurity Malaysia and INSPAM. Through INSPAM My Quantum Waves Initiative 2021-2025. Good luck in your future endeavor, and I wish you a fruitful and productive event. Thank you.
Thank you, Dato, for the speech. Ladies and gentlemen, we now invite you to view the montage video. Please welcome. Thank you to the Cybersecurity Malaysia and InSpam team for the montage. Ladies and gentlemen, now I would like to invite everyone to enable your screen camera for photography session. Please welcome. All right, ready everyone? 1, 2, 3. One more time. Ready everyone? 1, 2, 3. All right, thank you. Ladies and gentlemen, now I would like to invite Associate Professor Dr. Hishamuddin Zainuddin to chair our public talk by Professor Dr. Kwek Leong Chuan. Please welcome Dr. Hishamuddin.
Thank you, Faris. Can you hear me?
Yes, Doctor.
Okay, thank you.
Yes.
Assalamualaikum and a very good morning. Yang berbahagia Datuk Technologies Dr. Haji Amirudin bin Abdul Wahab, Chief Executive Officer of Cybersecurity Malaysia, Associate Professor Dr. Muhammad Rizal, Director of InSpam, Associate Professor Dr. Suryati, Head of Department of Physics, UPM, Dr. Chan Katim, Chairman of PWF EQuaLS2020, distinguished speakers and guests, colleagues and ladies and gentlemen. Welcome to the first session of this EQuaLS2020. So the first session will be a public talk by Professor Kwek. And Professor Kwek is familiar to many of us, but let me introduce him formally. Professor Kwek is a principal investigator at the Center for Quantum Technologies, NUS. He's also a co-director of the Quantum Engineering Program, NRF, and co-director of the Center for Science and Engineering at Nanyang Technology University. He's also the current Deputy Secretary General of the International Union of Pure and Applied Physics, IUPAP, and other appointments include Regional Representative of Organization of Chinese Physicists and Astronomers, USA, Secretary General for the Southeast Asian Theoretical Physics Association, Council Member for Working Group 5 IUPAP on Women in Physics, Council Member of Tan Kah Hee Foundation and International Society, Secretary General, Federation of Asian Physics Societies, President of the Asian Physics Olympiad International Board, and many more. Okay. His main research interests are foundation on quantum mechanics, including quantifying multipartite quantum entanglement, quantum cryptography, quantum computation, and atomtronics. So without further ado, Kwek, are you ready?
Yes, but I need to share my slides. Thank you. I hope you see the slides. Right, thank you, Hisham, for the introduction. And thank you, everybody, for coming so early for a talk online. For some of you, you put it very early in the morning, and for some people, it might be pretty late evening. Today, I'm just going to give a very simple overview. But as I was coming to the office this morning, somebody sent me through text messages a little snippet, which has 4 letters, sometimes 9 letters, but never 5 letters. Think about it. and for the rest of the talk, if you do not want to listen to it. Well, let me launch a little bit into the quantum information that has since been blossoming over the last 20 years or so. There have been several national quantum technology initiatives that has been initiated both in Europe and the United States and also in Asia. And you can see that this was a scenario somewhat like 2 or 3 years ago. There's quite a bit of changes since then. The United States has increased its share of investment in this area up to probably 1.2 billion. Canada has invested over $1 billion in the last decade, Canadian dollars. And China has more or less put in quite a bit, something to a tune of 1 billion USD. And United Kingdom, of course, has done a share, as well as many parts of Europe. Now, a little bit about quantum computing. So much of the hype in quantum information has been over quantum computing over the years. Part of the reason was spurred by the sort of understanding or realization that factorization could be done more effectively if we have access to a quantum computer. However, computing has always been a main tool of mankind since for ages. It started with the abacus, and then it goes on to some mechanical machines, Napier rods and stuff like that. To, for some of us, the slide rule. And slide rule was in fact used until the 80s as a main tools in school classroom to do calculations. In the 80s, when students go to the school, they will remember that they carry a logbook, and also they sometimes carry a slide rule. This is what the slide rule was for. It could do massive calculation for somebody very good at it. Now, mechanical machine was proposed way back in the early 900s, 20th century. And one of the machine which now rests as a museum piece in London at the Science Museum in London is the Babbage machine. Now, the Babbage machine was very successful for computing certain things, which was called a logbook. And you will see that this is the logbook. For some of us who went through the school system, the logbook constitutes a tool that we had to use in order to compute two very fairly big numbers. Now, that went on to become the analytical machine. And this was the blueprint of the Babbage analytical machine. Babbage never did manufacture or build an analytical machine. It was always on paper, and he spent a lot of money at that time to put it on paper. Something to a tune of several tens of thousands British pound, which constitutes somewhat like $500,000 by today's standard, million pound. But the blueprint in itself has some characteristics. It had many features of the modern computer. It had input punch card, control unit, output mechanism. It has a memory and a central processor. And it has computing language, which was equivalent to current assembly languages with loops and conditioning. So it has many, many features of the modern computer. But the modern computers then moved into the Hollerith card system. And I think some people will remember that when in the past, in the 80s, when we tried to do computing, we have to carry around a whole stack of cards. And this stack of cards, if you lose one of the cards in the middle, you are in disaster, because it's almost impossible to put them back. Of course, there's a way of numbering. You can number at the right-hand corner away from the scanning machine. So the card machine was first invented, and then it went on to become much more progress was made during the time of the transistor, when the transistor was discovered way back in 1940s. And this is the machine. And it gradually paved the way for integrated circuit, which we use nowadays in our computers. Now, if you look carefully at the transistor in the 1940s when it was first invented, you'll see that it was made up of very elementary stuff. Things like a paper clip twist around, and some wires and some materials. It was very crude in some sense, but it replaces a whole, it was a small enough device that could replace what was then called the thyristor, and which was the main component of the early computers. And that, in some sense, pushed the way for miniaturization. Without miniaturization, computers would be a huge monster. These were the huge monsters in the 1940s to the 1950s. Harvard Mark I machine, all the way to the British Colossus. So as the machines get smaller and smaller, so from 1 meter Babbage machine, we approaches the electrons and the devices have to be packed more compactly together. And so there is, in fact, this understanding that as we move towards the 2020s, we actually approach the atomic scale, but we never did. Actually, we are still very far away from that to some extent, in terms of real control. Microprocessors has, of course, made impressive improvement. They get very small today. And so the question is, when can they get really tiny? And if you follow Moore's law, the time is right now, but we never know. So how does a quantum computer work? A quantum computer works based on it could be based on ion, it could be based on atoms, and for that matter, it could be based on light particles called photons. And they appear as in states of classical computer appear as state 0 and 1. If you know our current computers, they all works on 2-level system, zeros and ones. But quantum computer, of course, works on energy levels of atoms or other features like spin of electrons and energy levels of atoms. So there are various ways of doing encoding. So what does it harness? It harnesses something like in this picture, the picture that I like to use in this respect. Here you see one of those pictures that you often see in illusion graphics. And what they do is that they ask you whether you see a young lady or an old lady. Young people typically see young people, and old people typically see old people. And so as you age, you probably see one aspect compared to the other. So if you look carefully at this picture, you will see an old woman smiling, for some of us, or a young lady with her head turned. Now, this is two aspects of the same picture. So it all depends on how you look at it. If you focus on this black line, then you see an old lady. But if you remove that black line, then you will see this as the neck of a young lady with her eyes turning this direction. So these are two aspects of the same picture. And we say that quantum mechanics, in quantum mechanics, we have a measurement, and every measurement puts you into a young or old state, but never both. So the young can be 0 and the old can be 1. But quantum mechanics at any time can allow you to have both pictures at the same time. This is another example, which is not so popular, but nevertheless is in the internet that you can extract. Do you see a man looking at you, or do you see a man turning away from you? So is a person looking at you, or is it a person looking to the right side? So again, these are two aspects of the same. So we say that one of the properties or features of quantum mechanics is that quantum state can exist in superposition. So until you do a measurement, you never know if it's one picture or the other. So again, if you look carefully at the shadings, you'll be able to see that there is one person looking at you on the one hand or the other. A classical computer, of course, works on the fact that you can have zeros and one, and so typical encoding could be 0, 1, 1. But a classical computer would be 0, 1, 0, 1, 0, 1 3 times, and this represents, in some sense, the whole perspective from 0, 0, 0 all the way to 1, 1, 1. So quantum computer therefore allows you a whole array of 8 numbers from 0, 0, 0 to 1, 1, 1 in just one representation. And even a classical computer needs to compute 8 times this quantity to give you 8 functions. Then the quantum computer can look at this superposition and operate. And of course, at any time, it gives you the function value corresponding to one of this, but nevertheless, it is operating in superposition. And therefore, it computes all 8 numbers effectively at any time. If you would like to get the functional value of all the 8 values, then there is actually no advantage between the quantum and the classical. However, if you use these functional values and try to make use of it to go further, to look for an exact answer, then you can make use of the result of this superposition and craft it so that there is a bright spot, somewhat like a double slit experiment, so that you refocus it on some bright spot, and the probability of getting that bright spot is then very high, and that will be our answer. So this is how quantum mechanics can use all the 8 possible paths and then somewhat recalculate, recompute, and formulate a single answer. Now, quantum mechanics also has another property. There's a video here, but I'm not going to play it, which is called quantum entanglement, and you can get it off the internet. List. And quantum entanglement is another property that is somewhat used, especially in factorization, quantum factorization algorithm. In that you can actually store whatever you have compute into another state. But quantum entanglement is not something new. For some of us who are in interpretation of quantum mechanics, doing measurement theory, for example, there is one perspective of what quantum mechanics is all about, which is that whenever you do measurement, you actually entangle your macroscopic instrument to your microscopic system. And so in some sense, your macroscopic instrument is already entangled to your microscopic system. And so this is a quantum phenomenon. Now, quantum speed up, quantum computer, of course, can do much faster. They can solve problems that are considered more difficult for classical computers, and they can break crypto systems based on prime number factorization. So these are three aspects of the incoming, forthcoming quantum computers. However, at the moment, I think Katim mentioned it this morning, we have a few qubits quantum computer, and even if they do perform fast, they are actually not as fast as we want it to be. And typically we cheat by saying that, oh, we have a chip now that can perform very fast compared to the ENIAC machine. But then that was the ENIAC machine in the 1940s. So we have to take quantum computers with a pinch of salt. The quantum computers we have today are very noisy, very lousy in general, and it doesn't always work. For some of you who have signed up for the IBM experience, you will have access to 5 qubits quantum computer, and I do encourage you to sign up for that so that you can play around with it. Much of our knowledge of quantum of classical computer today stem from the fact that some of us were daring enough to go and play around with the early algo and basic programs, even though those programming languages were really, really lousy. Some of us even play with assembly machines in the early days. Nevertheless, those give us the main knowledge to build on when we go further to build the current computer today. So I do encourage younger people to move into quantum computers if they have the interest, and to learn the tricks, because the future of, even though the current computers at the moment is nowhere comparable to any computer that we have, it is in some sense the futuristic computer, and we never know what we can get when we play around with it. New ideas will emerge. Now, factoring is another thing that is something that is very good with the quantum computer. If I ask you to multiply 13 times 17, I'm quite sure that you will eventually get 221 very easily. But if I give you the number 221 and tell you that it's made up of 2 prime numbers, then factoring turns out to be very difficult. It will take you some time, at least 13 trials, before you get to well, at least the numbers before 13, at least, before you get to this factoring system. But if I give you a slightly bigger number and ask you what are the 2 prime factors that constitute this number, then it becomes increasingly difficult. In this particular case, it's not difficult. You can try, and the square root of that is just roughly 100. So you only have to try somewhat like a few hundred before you'll get it. And you'll see that it's 89 times 7,019. So factoring in general is something that we can make full use of in this aspect. We can multiply something easily, but the reverse operation is hard. So you can lock your information very easily, but unlocking is hard. And this is the basis for what's called secure communication. One direction is easy, the reverse direction is actually very difficult. And so this is what we really want. Nowadays, quantum computer comes in various platforms. Nathan will be telling you something on superconducting qubits, I guess. And this is by far one of the most promising platform that quantum computers are being built. There are, of course, a competing one, trapped ions. Upcoming one, which is still in its very infancy, is silicon chip. The dream is topological qubits, and diamond vacancy is losing its battle. sometimes. But there are new systems that will always emerge, and some of these new systems, even if they cannot deliver a proper quantum computer, will deliver other quantum devices. It's always the case in history, and it will always be the case. So the timelines is maybe another 50 years before we can see a real quantum computer, because we are now at the age of 1940s or pre-1940s when it comes to the equivalent of quantum computer in classical computers. So we predict another 50 years. But in 50 years' time, do we actually get a quantum computer? That's a big question. In 1940s, if somebody were to ask you if you ever will get a computer, you wouldn't believe that you can get the computing power you get today. It is impossible at that time. So it's almost unimaginable. So where are the challenges? Well, today we have the noisy intermediate scale quantum computer. So NITS is era. And the vision is to solve real problems with real speed up and with real creativity in the next 50 years, or maybe less. So we need, of course, to scale up in terms of number of gates, and we have to scale up in terms of number of bits or quantum bits. It depends, of course, on our progress. Do we have a quantum integrated circuit? Do we have a quantum transistor? More importantly, do we have a quantum memory? We don't. So to a large extent, we need to build robust quantum hardware. The hardware that are based on not just real physical qubits, but also what's called logical qubits. Logical qubits means that you build many, many qubits, and but they are actually made up of many, many physical. One logical qubit is made up of many physical qubits. I will skip this. So this is a superconducting. I'll let Nathan take over. So this is what the refrigerator looks like. Much of the chip is actually inside this big refrigerator, and you send in microwave signals and interact with a little tiny chip. This is a different technology. This is Chris Munro in his lab building on the ion trap. So the ion trap also presents a slightly different technology, but and also slightly more robust, perhaps, qubit, but then harder to scale. Quantum computer now, of course, comes in various platforms. We need to consider interface. We need to consider the possibility of error correction, how to build the hardware, the quantum processor, how to build quantum memories, and so forth. And there are many, many other problems. Now, let me trace a little bit back on the history. The 19th century Industrial Revolution has laid the foundation for our current computer. And that led to, of course, to Babbage to dream about having a machine, which was only built in the 60s or even 70s for the Science Museum. And the need was to have accurate tables of trigonometry, the ties and interest rates. What for? A lot of these were needed because of the war. We need tables because we need to fight. But of course, many of these ends up in failure. At least the Babbage machine ends up in failure. The exploding population in the United States in the late 1880s led to the need to have population statistics. So the Hollerith machine was invented, the card reader, and that led to tabulating machines and to the railroad solving some part of the railroad problem. But the railroad turns out to be a disaster because it was not particularly successful. The First and Second World launched in and the First and Second War were crucial in the sense that a lot of money was spent fighting each other, but a lot of money then can be siphoned to computer research. And the ENIAC was in fact built during this period. The ENIAC, if we require government to approve spending of money to build a computer for peaceful purpose, no government effectively may actually agree. But to spend money for war was important because it's national security. And therefore, a huge amount of money will pour into war efforts. And some of this money, a fraction of which, say several millions, were used to build ENIAC. So ENIAC then moved on to a more commercial machine like the UNIVAC and to the mainframe in the 1960s. But it was the need for firing tables, it was need for cracking codes. There was the Eisenhower election, now we have the Trump election, Trump-Biden election. Maybe we can predict, but of course this one could be predicted with an abacus. And also we have other machines. So we see that we need crises to build computer. So what are the crises for quantum computer? Do we have a crisis? Crises are essentially needed sometimes for big projects. When there is truly quantum computer, when is it truly going to be built? At the moment, we have heard of the Google computer, maybe 72 qubits, maybe even more, but nevertheless, it cannot be a programmable computer at the moment. Now, so this raised the question of if no quantum computer is going to be built, then there's no threat to factorization, and therefore there's no threat to quantum security. So quantum security or quantum cryptography is never needed. So it becomes a chicken and egg problem. And what happens if all the current industrial investment in quantum computer fail? Do we end up in a quantum winter? Maybe, but science takes on like quantum mechanics in steps of progression. So perhaps the intermediate goal might to move towards better simulators. Feynman has this very crude remarks that he made, that nature isn't classical, endemic. If you want to make a simulation of nature, you better make it quantum mechanical. So we have to have intermediate goals. And by then, can we trust quantum simulators? Well, I leave these discussions to you. You can, this is an old paper by Marchet Levenstein. So there are various platforms for quantum computers, including putting atoms into hollow fibers. But nevertheless, it's an area that we need to explore. There are photonic simulators. There are also ion traps. There are also neutral atoms, but they constitute a lot of this simulation. But simulators at the end of the day are just simulators, and they are not quite the real things. One has to understand that there is a difference. Learning how to drive on a simulator is not quite the same thing as driving on the road. Towards better encrypted communication is another area that quantum technologies can provide, and in fact is one of the most mature technology at the moment. And one of the schemes for so-called quantum communication stems from this guy at the top left-hand corner, Arthur Eckert, who, and it all of course stems from the fact that human has since antiquity has had two inherent needs: to share and communicate information, and to communicate information so that as few people as possible can know. So this was 4,000 years ago, when the Egyptians tried to communicate messages through hieroglyphics. And a lot of this were secret codes. This is in fact the Papyrus or Ani, the Egyptian book of the date. So cryptography and in itself has long history. It started from the Greeks, cipher, to the Arabics, and to the Second World War, where the German soldiers used what's called the Enigma machines to fool their enemy. However, just as humans are good at keeping, inventing devices to keep secrets, there are also humans who can try to decode messages. And this was a bunch of Polish scientists led by Mariam Adam Rejewski, who were able to do code breaking in the Second World War. Now, how does cryptography work? Well, a lot of cryptography is not sending secret messages. A lot of cryptography is really about setting up common rubbish. So the one-time pad, in fact, is an encryption method that was invented to establish two random secret keys. And so the idea was this: suppose you have a message called plain text, 01001, blah, blah, blah. And you have a random array of number in red, 011110110101. Then you can just simply add the two numbers. 0 plus 0 is 0, 1 plus 1 is 0. Why? Because this is the way we do addition, the first column of binary addition. So if you have 0 and 0, of course that's 0. 0 plus 1 is 1. 1 plus 0 is 1. But 1 plus 1 is 0, carry 1. But the carryover is never a sin. So that's why 1 and 1 is 0. And so if you do this addition, then of course, this is message added to rubbish. Then what you get, of course, is rubbish. And since this green part is rubbish, you can always send it through any channel you like. You can even broadcast it. And then the other party who has the key, common key, can just decode it. Why? Because you'll find that message plus rubbish, we'll come back to that later. So Vernon cipher was in fact patented way back in 1917. And so the idea of how to distribute is common rubbish. So you need common rubbish, red one in this picture, is to do it this way. So this is how classical communication works. You establish a secret key, so that was the red one, and you deliver it to the other side. And chances are, if you do it properly, then you can establish this classical communication. Now, quantum theory, of course, allows for a different correlation to exist. And that is, if you flip two coins and these two coins are entangled, then if one side of the coin reads 1, then so it does the other. So it's 1, 0, 1, 1, and so forth. So, but of course, this is establishing of common rubbish. We have not established any information between Alice and Bob. And this common rubbish, once it's established, allows you to distribute the key in a quantum mechanical way. So these two keys, which was couriered by somebody in the classical channel, is now done quantum mechanically. And the idea of this one-time pad is this: you have a message, and then you have a key. Then you have this rubbish. The key is rubbish, and so you get rubbish. And this rubbish is exactly sent between Alice and Bob. So message plus rubbish give you rubbish. So you send the rubbish over to Bob, and Bob gets this message and rubbish, and message plus rubbish is added to that common rubbish. So this rubbish and this rubbish are the same. And the interesting thing about the operation we had earlier on is that rubbish plus rubbish gives you 0, and therefore you get back your message. So this is the main message. Rubbish plus the same rubbish is equivalent to not adding anything at all. Remember, 0 plus 0 is 0. 1 plus 1 is 0. So whether you add 0 or 1, you get 0. Now this is a video. I'm not sure if we have time to play it. This is a video from Toshiba. Not sure if you can hear it. Oh, sorry. So I was told that you can't hear anything. Okay, so anyway, you can I hope you can hear me now. You can watch this video online. It's in YouTube under Toshiba. So you go Toshiba quantum key distribution, you should be able to get it. But this is the device, pretty big actually. But nevertheless, it's much smaller than the earlier ones. So you have the encryption. Most of the chips are the lasers and all the gadgets are all placed here. Now, there are, of course, different quantum key distribution. The one we know of makes use of, in terms of zeros and one, you can use actually a horizontal and vertical polarization, but you can also use other systems, so-called continuous variable based on coherent state. But we'll not talk about that. So there are actually two different types of quantum key distribution. The one that has gone through secure proof is actually the discrete variable quantum key distribution. The continuous variable quantum key distribution is a lot less understood in many aspects. Okay. Alex Ling at the CQT has actually been thinking for some years of launching key distribution through a CubeSat, and I think they have made some progress in recent years. CubeSat is just a 10 centimeter by 10 centimeter by 10 centimeter cube, and it uses very little power, hover in space, and whenever it's directly above the pointer where you want to communicate, then you can actually allow for that communication. This was actually proven. The entanglement part was proven to be possible on a nano satellite. So this was the 10 centimeter CubeSat, and the rest of the experiment was done on the 20 centimeter part of the. So this. But of course, recently there can be other advancement, and one of those advancements is making it smaller. And so we have shown that this is indeed possible. We have reduced these benchtops of accessories for quantum continuous variable quantum distribution to just a tiny little chip that is roughly slightly more than 5 millimeter in length and about 2 millimeter in breadth. And of course, these are the controlling devices, but nevertheless, the real chip is of this whole thing is really tiny, using silicon photonics. We have also sort of miniaturized it for discrete variable quantum computing on a system called Measurement Device Independent Key Distribution, MDI-QKD. And this is the device that was built, and it's really also very tiny. So why do we bother about miniaturizing? Now, the miniaturizing allows you to place your quantum key distribution on our handphone. In the handphone, if you be careful, carefully rip it apart, you will see that there are many, many layers, actually, tiny nanofilms. And these nanofilms, nano layers, very thin layers, allow you to capture many, many chips, many, many components. And if you can miniaturize quantum key distribution, you could make it an everyday means of communication. So perhaps we might be able to incorporate into a mobile phone. At CQT, they have been able to compact a random number generator. But quantum technology, of course, offers much more. It offers better clocks as well. So we have more precision. The history of clocks is long, and it starts from the ancient obelisk all the way to modern day quartz machines. But for high precision, we'll need atomic clocks. And atomic clocks, atomic fountains have been devised in various national laboratories in the world. Cesium clock has also been devised, but these are very, very big objects. And so one step further would be to miniaturize these clocks into small levels. And small clocks are now being built by the group of Murray Barrett at the National University of Singapore. And recently on lutetium ion, they have managed to show that in principle, you can get more precision. And also this technology can be harnessed to make into chips, tiny chips. So the idea is to have this whole room of gadgets miniaturized into tiny little chips here. The process is still being done. It's still experimentally looked at. So I'm going to skip some of those. So you'll see that a quantum system, aside from computing and aside from communication, also allows us to do what's called sensors. One of the computing platforms that I mentioned earlier, the nitrogen vacancy atom, was not deemed to be very suitable for computing, has shown to be a very good quantum sensors in the sense that it can detect very tiny vibration through its various vibrational modes. So aside from the doing computing, aside from doing communication, we now try to feel and hear and see with a quantum device. And these are quantum clocks. We envisage that for the next 5 years, this will be heavily invested. Gravimeters is another sensors because we would like to sense underground objects. GPS-free navigation is another one. Magnetometers for brain imaging, and also another low-hanging fruit, quantum radar. So it's called light detection. Kaibongs has a YouTube video which you can listen to talking about quantum sensors. So I leave you to look at. So just like laser was discovered in 1960, optical fibers in 70s, integrated circuits in the 50s, we aim to have global communication network on a quantum level. So this is a futuristic dream. Whether we can do it successfully or not depends, of course, on our perseverance. It depends on our ingenuity. It depends, of course, on global efforts. Wolfgang Ketterle has said this, that the people in the entertainment industry didn't discover laser for DVD and Blu-rays. That was the work of scientists. Dentists didn't discover X-ray for improved medical imaging. That was again the work of scientists. Michel Lukin also said the same thing, that clocks are important devices for driverless cars in future. We'll need to build and invest in science. Basic science is what keeps the whole technology going. So lastly, let me say something from Sesh Ahosh. It is hard to make prediction, especially for the future. But one thing is for sure, with basic research, novel technology cannot be invented without basic research. And the past teaches us that wonderful application always emerge serendipitously from blue sky research. Quantum information. Currently, of course, we see quantum computer, quantum crypto devices. We may, in the next near future, be able to tie up with 2D materials to come up with quantum materials, novel materials, quantum sensors, atomic clocks, atoms replacing electronics devices, and what else? We don't know. It's just a matter for young people to explore, to be creative, to be curious, and then you will then lead forward what this question mark is going to be. The OSA report recently have the following timelines. I don't believe so much into roadmaps and timelines, although I write many of these roadmaps. But nevertheless, some of this have been planned all the way to 2050s, 50 years from now. I'm not going to be around to see it. Maybe some of you will see it. But in any case, it is your dream. And without dreams, nothing can be realized. Thank you very much. Be a quantum mechanic.
Thank you, Prof. Quek. So I think we are now open for Q&A. I believe.
Good morning. I would like to ask the first question.
Thank you.
All right. Okay, Jasne.
Hi, Prof. Quek. This is Rizal from.
Hi.
Yeah. Okay. I would just like to ask a very managerial question. This is regarding to the security 2007 initiatives, whereby it's on the internet already. It's on Wikipedia. That the NUS under security managed to get like 100 millions of Singapore dollars from the government. So the question is, how did the group of scientists manage to get the buy-in from the government? Because as we know, a very future-looking science to obtain huge allocations for research is very rare, especially when there is no return of investment in like 3 years or 5 years or 10 years even. So can you just share a little bit of experience? What was the main point such that the government of Singapore actually allocated this and believed in the dream? Thank you.
Right. Thanks for the question. I believe a lot of this question, a lot of this answers goes back to, well, at least in the Singapore context, it goes to a person called Dr. Tony Tan, who was at that time Deputy Prime Minister of Singapore and subsequently became the president for one term. He was a person who was in the sciences. So he was a physicist and or mathematicians later on for his PhD. But nevertheless, he was interested in science. Now, it is important for politicians, therefore, to have good scientists. So you need, what is important for us it takes a lot less convincing when there is a scientist on board in politics. They paved the way for a lot of these obstacles in some sense, this resistance. I'm quite sure there are a lot of politicians whose children aspire to be scientists. Now that also helps sometimes. So if you can talk and make sense to some of these scientists and they buy your idea, it makes the work all the much more easily, your work more successful in that sense. So one has to explore. Otherwise, we need to train students. They will all be very smart. Some will stay in academia, but some of them will not. And hopefully one of these bright sparks will go into politics. And that will be the day when this guy will decide to lay the foundation of all the quantum science in the country. Yeah. So this was the way it started. Without Tony Tan, I think a lot of this science effort would not have been possible. And he was a scientist.
Yeah, what about the buy-in? I mean, of course, there has to be a narrative, right? Why quantum? So why quantum?
There were a few options, having a scientist on board as a politician helps, of course, in the sense that being a scientist, you will never be away. You'll never be stuck in other branch of science of administration for long. In the sense that although you are a politician, you will always indulge yourself in some science in your free time. In that sense, the current Prime Minister of Singapore is also very much a mathematician at heart. So you can see that he does some programming at times. So they are all interested in the daily life, not just in politics, but also in the very basics of entertaining themselves with science. So this is important. To buy the politician in, first you must be convinced that it is good for the country. Without being convinced yourself, it's very hard to be a salesman. I've met many salesmen who try to convince me to buy machines, but they're not very successful because they don't know what the machine is for. So selling machines just means that you need to be proficient in what you're doing, and you must seriously, at the end of the day, decide something. A very important question. Is this going to bring the country forward? If you are convinced this is the way, then it doesn't stop you from trying. You can encounter many failures, but one success will do. So this is what we need to do. Now, when when I always have great respect for Hisham, Professor Zainuddin, because ever since 2005, I think 2007 was the first time he started his expository quantum lecture series. He has been trying to move the country forward with a series of very serious lectures, inviting people on board to give talks to the local students. I think this is a very commendable effort. The country should recognize such talents, such people, such contributions, and not just push it aside. It is important to realize that within Malaysia itself, not talking about Southeast Asia, Malaysia itself has a lot of very good academics who are seriously interested in science and who are seriously interested in the future of the country. So we need people like that. We need to listen to them, and we need to bring them together, and as a collective voice, show the government that what is the best way to go forward. The government may or may not know what is the best way in terms of technologies, but the people in the field should know, and we should be the one pushing for it. Even if it's not successful, it doesn't matter. We will try. Yeah. So that this is we are working for the people, not the government.
One easy question: was there an economic narrative, something that was sold to the government, the potential to become an economic hub or something?
When the quantum technologies, that's why the word was technologies, wasn't quantum information. So there was an economic perspective to it, but when we first pushed for it, it was just to rally a group of talents. The government realized that we need a certain number of core people that are doing good research within the country, and this was the impetus. Yeah. So that wasn't so much on the negotiation table, but of course later on it becomes more and more important. We have given you so much money for the last 20 years, and you now show some economic returns. So that always becomes a factor, because the money comes from the people, and the people needs to see the returns. So there's the income tax of the people, so the people needs to, they're the voters in some sense, have to see the returns. Otherwise, they'll be wondering, why are we voting you in a democratic country? Sometimes it's a lot better to have a dictator who decides everything.
Okay, all right. Okay, thank you very much.
Thank you. Yeah.
Okay, thank you, Dr. Reza. Let me move from this awkward situation.
Can I have a question?
Please.
Yeah. I'm sorry.
Yeah.
Okay,
yes.
Go ahead.
Yes, correct. So
yes.
I'm sorry. I just enter your presentation half, but then I
That's
just need to know. I just need to know that now actually we most of the protocol goes to the twin field QKD. I mean, even the continuous variable also, being implemented in twin field QKD.
Yes.
So, is it that is there the possibility that almost all the system will be implemented on twin field QKD, or there will be another method?
There will be another method. We believe there will be other methods. Yeah. So the twin field does not have the final say. But it's very interesting to note that between 1991 and 2002, when the continuous variable QKD was discovered or implemented, there were no other proposal. For about 20 years or so, nobody comes up with new idea until Hoi Kong starts the idea of MDI QKD, and then that starts the next level of research. Yeah, and I have said earlier on, research always comes in steps. Quantize.
And I seem that they have some small paper that, I mean, do also working on something like modulation techniques, CDMA, MDM, something like that. Was there is also another part that will be explored after this? I mean,
yeah,
it's
it's
something like
anybody's
continuous
guess.
variable, because it's a come from the communication. I mean, communication part. And then after that, explore into the quantum system.
Of course, in terms of implementation, it doesn't matter which one of these come into play. The establishment of a quantum key distribution will eventually be combined with classical cryptography in a mixed match session, mixed mesh sort of way to create what's called a national encryption codes, so that no other country have unique can guess whether you're using classical or quantum at any time. So you mix them in an appropriate way, and that recipe of mixing and blending become your national recipe. So nobody can guess. In some sense, the future cryptography will not fully be quantum, nor would it be classical. It will be a mixture of both. Yeah.
Thank you, Prof, for your kind comments.
Yeah, I have a question.
Uh-huh.
In relation with quantum information and specifically in quantum computing, the current challenge are primarily experimental or theoretical?
The research should be primarily experimental or theoretical. Is that right? You're asking?
Yes, the current challenge is experimental.
Well, current challenge is both. I would say current challenge will be both. In terms of experiment, in terms of computing, so there are, it's a large area. For computing alone, in terms of experiment, we need a memory. That is non-existent. Yeah, so this is one of those. And other devices, in fact, there are other devices in terms of interface, in terms of encryption that needs to be exploited. Error correction, for example, on the devices. If you want to go forward in terms of better quantum computer, we need better encoding. So in terms of hardware, not in terms of software. Software, there's so much we can do in terms of error correction. But hardware quantum error correction is still an unexploited territory. So this is a very big area. In terms of theory, there's still a lot of things. So aside from prime number factorization, aside from Shaw algorithm, Grover search algorithm, what else do we have? In terms of maybe we have an algorithm for solving linear equations. Maybe we have a variational algorithm for finding the ground state energy, which in turn have implications in chemistry. But all these algorithms, at the end of the day, we still need to find more algorithms that can distinguish a quantum computer from a classical. So in terms of theory, there are still a lot. What sort of sampling algorithms do we have? Because currently, of course, a lot of these quantum supremacy things relies on sampling. To prove that the Google computer was better than the classical computer, they do a sampling test. So there are lots of theory questions. There are also theory questions in terms of basics. How do you certify if you have a quantum computer that it is a quantum computer? So certification is a very big problem. In terms of looking at novel phenomena. Can we use a simulator to say that we really have a novel phenomena that is not predicted in theory? This is also a good question. Yeah. Because if you can do calculations and say that we expect certain novel phenomena, and then we see the novel phenomena, it's like teaching the preach audience. I mean, you already knew it's going to happen. But if you can play around with a quantum computer and discover things that you don't expect, then that is something new, truly new. In fact, polarization was something that was discovered experimentally in some sense. Yeah. A Polaroid, for example, not polarization, but a Polaroid device. So lots of things to do, lots of things to look at. And I believe it is an area that young people can put in a lot of their energy into and see a lot of returns. Yeah. I believe there's a lot of things that one can get. Quantum sensor, for example, is also another big area. None of these quantum sensor actually works at the moment. Yeah, there are lots of quantum sensors, but they cannot be much better than the classical sensors. Our classical sensors are already very good. Yeah, with very good precision. Can the quantum mechanics offer that tiny little edge? That's a big question. But then it does not stop us from pushing it. Very often we need to clear the hurdle. It's only at the next step that you see a distinct difference between quantum and classical. At the moment, they are matching, neck to neck. Yeah. So when they are neck to neck, you can't tell the difference and you don't care. But when they reach the next step, then you see the difference. The classical stops there, but the quantum is at another level.
Okay.
I hope it answers your question.
Thank you so much.
Yeah, thank you for the question.
There's a question in the chat, and also that somebody is raising the hand. We will give Sandeep to ask the question.
Yes, yes. You ask a question. I try and see if what is the question on the chat.
Maybe we can have Sandeep.
Yeah.
You can go ahead.
Okay. Hello, Professor.
Hi.
Just and namaste from Nepal. I'm from Nepal. So I'm asking, as you said, every time if we compute any phenomena by using quantum computers, and we expect something new, something bigger, and something in a fast way as well. So how can we correlate with the calculations or the every experimentation calculated from the classical computer with quantum computers? So
okay, I must apologize if I give you the impression that quantum computer can do much better than a classical computer. It does not. At the moment, a quantum computer can do marvelous things, it appears, but nevertheless, compared to a classical computer, it is still like a little baby talking to an adult. Now, but it has potential. You can see already the potential in this tiny little baby that is growing up. If it grows up properly, provided it grows up, all babies grow up to be good and bad people. And if it grows up properly, then it has the potential to do a lot of these computations in tandem. So a quantum computer has superposition, ability to do superposed state, which means that essentially it's like a virtual parallel computing. And so we know that even in classical computing, that parallel computing can do much faster than sequential computing. And so doing parallel computings with the right task and the right sort of work will allow you that edge in terms of computing power, which you have not seen currently in predicting experiment. Does that answer part of that question?
Thanks.
The other part to that question is, what we have not fully explored is to look at atoms on the two-dimensional surface seriously enough. Now, very often we resort to the computer to do a few atoms simulation. But a quantum computer can easily load a few thousand or a few millions quantum atoms into this 2D lattice. And for that, no classical computer can compute for you the answer. Question is, a quantum computer will give you the answer, yet you do not know what is the real answer. So the question is, what is the real answer? How do you believe what the computer calculates is correct? Or how do you believe what you have seen is correct? Now the question is boils down to that. But then again, in nature, if you look at something and you see something, how do you know you have seen it correctly?
It's like an illusion. Everything
Yes,
like
yes.
a light. For example, light. If we relate with, if we go into the quantum way, it's a photon. Even
Yes.
for a photon, there is also illusion. So how can we standardize every result with the, for example, if you do any practical in a classical way, I'm just asking, if you do any practical and if you have a result final, yeah, we correct that answer, and if we can correct as well as we can compare that answer with the standard one, then we can visualize, yeah, that's my error, yeah, I'm whether I'm accurate or whether I'm precise. So the same thing happen for quantum computers as well.
Yes. I think we lost him there.
Okay, probably we have another question from another participant. Can we give
Sure,
room
sure.
to the, okay, let me just read the last few questions. Quantum computing with respect to the ability to do superposition and entanglement. Are we heading towards the boundaries of human logic as we know it? This is from
no.
Sarah.
We are not reaching. Yes, I was answering the first question from Sarah.
Sorry.
Yeah. I do not think we will lose our power to predict, even with a quantum computer, and I don't think we will lose any of this human curiosity in some sense. So that the question was, I answered the question, then I lose the, even with superposition and entanglement, we do not head towards the boundaries of human logic as we know it. Human logic has no bound, at least as far as we know. History has shown that when we reach the boundaries of it, we create new logic. And that's the amazing thing about human power. Now, computers are now built to mimic human logic. Now, can computers replace human logic? That is another big question. Yeah. So with superposition and entanglement, can we build machines that supersede human logic? Is a big question. Is anybody guess? I don't know the answer.
Probably this will be the last question before we move to the next session. Jasny, do you want to answer to ask the question directly, or you want me to answer to read it? Jasny?
Jasny can answer. Jasny is one of the main experts in quantum cryptography.
Okay, let me just read it. if there has any been
recent interest in quantum in terms of quantum biology.
Yeah.
Quantum biology was an interesting topic some years ago, and then it has subsided. Eventually, it should resurface when we can use quantum computers to overcome quantum chemistry. So I believe it just takes time. At the moment, a lot of these biological systems are too noisy, too wet for any quantum phenomena to exist or to be seen, to be observed. But we never know if there will be future advancement in that area. It's always an area to watch out for. Primarily because of two things. We physicists are simple objects. We think in simple terms. All human bodies are points, and we move in straight lines. But biological systems are never so. Biological systems are complex. Biological systems have complicating equations, complicating sets of equations. And so, but it is the real problems. And so we need to answer such biological problems at all stages. So it will do a comeback, even though it has sort of subsided in the last few years. That's my feeling.
Okay, I think that's probably it. Thank you, Prof. Quek.
Thank you, thank you.
The very interesting talk and very stimulating Q&A session. So, so by the end of this session, we are going to go to a different link for the next session with Professor Langford. So participants are required to use the link that was in the handbook, okay, a different link. So I think let's all thanks Professor Quek.
Thank you.
Okay, thanks, Quek.
Thanks, bye. Meet you in the other link.
All right.